In this video, we're going to learn about the greatest common factor, which we also called in short the GCF. Let me give you an example to demonstrate what the greatest common factor is. So I'm going to take two numbers, let's say 24 and 60. Now I'm going to tell you that the greatest common factor for 24 and 60 is 12. So GCF equals 12. Now, what is that special number? Well, it's called the greatest common factor for the following reason. Number 24, I can rewrite as 12 times 2. And number 60, I can rewrite as 12 times 5. So notice how 12 is the part of each number. It's a factor of 24 and it's a factor of 60. And that's why it's called common, so it's the same for both. It's common in both numbers. And greatest means that it's the largest number like that we can find in 24 and 60. In other words, that's the largest common factor we can find in 24 and 60. But what if we're asked to find the greatest common factor? How do we find it? How did I find the number 12? Well, there are different ways to do it. And one way is to think this way. Well, if 12 is present in both numbers as the factor, it means that I can divide both of them by 12. So 24 I can divide by 12, I'm going to get 2. And 60 I can divide by 12, I'll get 5, right? So one way to think about GCF as the largest number that we can divide into 24 and 60. I'll say, so that is the largest number that divides 24 and 60. So this is one of the ways to find the greatest common factor, especially if you work with the small numbers. So just think about the largest number that divides the 2 or 3 you're given. But what if you're having a hard time to think of the largest number? Or what if you found a number that divides two of the numbers given? Let's say if I look at 24 and 60, I know that 2 divides both of them, or 4 divides both of them. But how do I know it's the largest one? Because our goal will be to find the largest. Well, then there is another way you can use, and with that method, you're guaranteed to find the largest common factor. So that method goes like this. You take each number and you split it up or decompose into prime factors. It's called prime factorization. And the way you do it is the following. So you start with a number and you need to split it up any way you can. So 24, I can think about 24 as 6 times 4, right? So I'm going to write that down, 6 and 4. Okay, then I'm going to take each and I'm going to try to split up each number. 6 can be split up into 2 and 3. And that's the only way, right? And now as I look at 2 and 3, those two I won't be able to split up. I won't be able to represent them as a product of two other numbers. Well, because they're called prime. So prime numbers can be only written as the product of 1 and themselves. So we won't be able to split them up any further. So I'm going to circle them because it's kind of like dead end here. Now if I go back to 4, 4 can be split up. So that's 2 and 2. 2 times 2, right? But once again, 2 is the prime, so I'm not going to be able to split up any further. So once I get all the way to the point where I can't split up any numbers, and it means that I'm looking at the prime numbers, then what it means is that 24 consists of a product of those numbers. So it's 2 times 2 times 2 times 3. And we can double check that. If we multiply those, you cannot see. If we multiply those out, we're going to get 24. So it's called prime factorization. I'm going to write this down just for the record. Prime factorization. Now we'll try it for 60. And keep in mind that you can start splitting up the number any way you want. And if there are different ways you can start, for example, here I can start as 6 times 10, right? Or I can do 2 times 30, or I can do 4 times 15, so there are different ways. Guess what? No matter how you start, at the end, you're going to get exactly the same collection of prime numbers. So don't worry about that. So let's do 6 times 10. 6 times 10. Now, each I can split up, right? 6 is 2 times 3. Now, those two are primes. I cannot split them any further. I'm going to circle them. And 10 is 2 times 5. 2 times 5. And again, these are also primes. I cannot split them further, so I'm done. It means that 60 is represented as the product of 2 times 2. I'm just putting numbers in order. You don't have to. I'm just kind of doing it out of habit. 2 times 2 times 3 times 5. Again, if you multiply those out, you're going to get 60. So that is prime factorization of 60. So the next step would be to spot common factors, like pairs of prime factors within each number. So it's easier for us to do that. I'm going to rewrite 60 here. It's just going to be easier to look at them right next to each other this way. And I'm going to start circling pairs of numbers. So I have 2 and 2. Then I have another pair of common prime factors. And do I have another pair? Yeah, I have another one right here. So 3 and 3. That's it. I don't have any other pairs of common factors, common prime factors. So once I find all the common prime factors, then this is how I'm going to obtain GCF. From each pair, I'm going to use the numbers. So it's 2, pair of 2s. Here's another pair of 2s, and then here's a pair of 3s. So I put 2, 2, and 3, and then I will have to multiply them. So now as I multiply them, I get 2 times 2 is 4, and then 4 times 3, that's 12. And that's the GCF, the one that, we knew is the GCF from the very beginning, but it's just the second way of finding the GCF. It takes a little bit more time, but this way you know that you got the GCF. Again, another way is just to think, what is the largest number that divides the given two? So let's practice that. Let's look at a few examples. So let's say find example. Find the GCF. And we'll do A, B, and C. Okay, so A. Let's say we have 36 and 54. Okay, so to find the GCF, one way is to think about the largest number that divides 36 and 54. And if you're good with numbers, if you're good with multiplication table or math facts, then you might be able to think of the right number. If you're having a hard time, and I'm gonna say it yet. Instead, okay, so hopefully you can think of a number. If not, we're gonna use this longer method. We're gonna use prime factorization to find it. So to do that, I can just do it right away, right here. We're gonna start splitting up the number into prime factors. So 36, how can I split up 36? I think it's one of the ways, it's 9 and 4. So I'll do 9 and 4. Then 9 I can split as 3 and 3. Both are primes, because I cannot split them up any further. And then 4 is 2 and 2. Again, they're primes. So I got this 36 is 2 times 2 times 3 times 3, right? That makes 36. Okay, how about 54? 54 is, what is this? 6 and 9, right? 6 and 9. Now 6 I can split as 2 and 3. And 9 I can split as 3 and 3. So then 54 consists of 1, 2, and then 3 3s, right? Like that. Okay. Now I will have to find pairs. So here's one pair, and that means that the GCF will get 2. Let's see. 2, I don't have any other 2 in 54, but I can see a pair of 3s. So that's another 3 in the GCF, and I can find another pair. So these are all common prime factors. But if we put them all together and multiply them out, we're going to get the largest or the greatest common factor. So that is 2 times 3, that's 6, and 6 times 3, that's 18. So maybe some of you thought about 18 from the very beginning, right? That's the largest number that divides 36 and 54. I can write it here. So another way to think about it, the largest number that divides 36 and 54. The GCF, the greatest common factor. Okay, so let's do example B. Now in example B, let's look at three numbers. Can we find GCF not for two but three numbers? Yes, we can, and idea will be similar. So we'll use 28, 32, and 40. You can start thinking same way. What is the largest number that divides all those three? Well, I can see that they're even numbers. So since they're even numbers, it's guaranteed that 2 divides all of them. But can I find something higher than 2? Think about it. And we're going to check that by using the prime factorization. So we're going to split each into prime factors. So 28 is 4 times 7. Now 4 I can split as 2 and 2, and I circle them, they're primes. 7 I cannot split up, right? So that means that 7 is prime. It is prime. So 28 I can write as 2 times 2 times 7. Let's try 32. So 32 I can do 8 times 4. Now 8 is 4 times 2. 2 is prime, but 4 I can split further. That's 2 and 2. Those are primes. And 4 is 2 times 2, so 2 more primes. Okay, so it looks like 32 consists of 5 2's, right? So 32 is 2 times 2 times 2 times 2 and another 2. Okay? And then finally 40. So I think the easiest way is to do just 4 times 10. 4 and 10. 4 is 2 times 2. 10 is 2 times 5. Both are primes. Okay, so 40 is 2 times 2 times 2 times 5. Okay, so we found prime factorization of those three numbers, and now we have to find not pairs but triplets of same factors, same prime factors. So I'm going to be circling 3 same factors. I have 2, 3 of 2's, so GCF will have 2. Can I find another triplet? 3 of the same prime factors? Yeah, here it is. 1 more. So it's going to be another 2. Can I find another triplet? I don't think so. I have 7 here, but no other numbers have 7. I have those 2 have 2's, but I don't have the third 2. 28 doesn't have any other 2's left. So yeah, no more triplets, right? It means that that's all I will have for the GCF, and that's 2 times 2, which is 4. So the GCF is 4. And that's the largest number that divides 28, 32, and 40. The largest number that divides 28, 32, and 40. Like that. Okay, and then let's try example C. In example C, we'll take the following numbers. Let's do 32 and 45. So what is the largest number that divides 32 and 45? Okay, start thinking about that, but we'll check that using prime factorization. Can you find the largest number that divides 32 and 45? Well, let's try with prime factorization. 32, we just did it, right? It's 8 times 4. 8 is 4 times 2. 2 is prime. 4 I can split as 2 times 2. And here I can split that as 2 times 2. Okay, we already did that, so I remember from my previous example, so that's 32 is 2 times 2 times 2 times 2, 5 of those, like that. How about 45? 45 is 5 times 9. Now 5 is prime, I cannot split it up, any further, but 9 I can. So it's 3 times 3. Those are primes. So 45 is 3 times 3 times 5. Okay, so right here. This is prime factorization of 32 and 45. And in order for me to find the GCF, I'll need to search for common prime factors, pairs of the same numbers, right? So can I find any? Looks like I can. So I have only 2's in 32, but they're not a single 2 in 45, right? So I cannot find anything that they have in common. So no common prime factors. What does this mean? Do I have a GCF, or maybe we don't? Well, actually, we're always going to have a GCF. But if it happens that we cannot find any prime factors, common prime factors like that, well, the GCF, I think what can divide 32 and 35, and that was where I started, right? Maybe at that point we thought, well, that nothing really divides 32 and 45 at the same time. But there is one number that can divide any given number, and that number is 1. Remember, we can divide anything by 1. And in this case, when we cannot find any other common factors, well, 1 will be the GCF. So in this case, GCF is 1. That's the only number that divides 32 and 45, and that happens to be the GCF. So that's how we think about it. Now, these are examples where we had to find the GCF for numbers. How about variables? What if I have variables? Actually, with variables, it's even easier and quicker. So find the GCF. And let's say x cubed and x to the 5th power. What's going to be the GCF? We're going to try to follow kind of like the same process. In other words, we're going to split each variable into factors. But how do we do that? Well, what does it mean that I have x raised to the 3rd power? Well, that means that I have x times x times x, right? And then what does it mean that I have x to the 5th power? That means that I have 5 of those x's multiplied by each other, right? Like that. And if I follow the idea of finding common factors, then GCF, to find the GCF, I'll have to circle pairs. And here I can see that, well, it makes sense that I can find 3 pairs, right? I only have x's here. And if I put each in the GCF, what's going to be the GCF itself? It looks like the GCF is going to be x times x times x, but that's same as x to the 3rd power, right? Well, hopefully this process makes sense, even though we don't have to do it every time. So what's interesting and what makes this easier than to work with numbers is that when we have variables and they're the same variables, the GCF will always be that variable with the lowest power. So if I have x cubed and x to the 5th power, I have just to find the lowest power. So I'll make that note. The lowest power, well, among the ones that are present. Okay, so let's try it one more time. Then we're gonna skip this process. So with variables, we can just jump right into writing the GCF. So how about if I have 20y to the 3rd power, 10y to the 2nd power, and then 15y to the 5th power. What if I need to find the GCF when I have both variables and the coefficients? Then we have to do one thing at a time. So first we have to focus on the numbers and find the GCF for the numerical part, for the coefficients. And then we have to switch to variables. I specifically chose, it's kind of simple numbers here, so maybe we can right away find the GCF. So when we look at 20, 10, and 15, so what's the largest number that divides 20, 10, and 15? You probably can guess that it's 5, right? So then GCF will have 5. That comes from 20, 10, and 15 common factor, the greatest common factor. And what's going to be the GCF for the variable part? Well, it's going to be that variable, y, but raised to the lowest power. So then I have to check all the powers present and find the lowest one. If I have powers 3, 2, and 5, well, the lowest is 2. So the GCF will be 5y to the second power. So that is the lowest power among present powers. And then 5 is the largest number that divides 20, 10, and 15. Like that. So that's how we think about the GCF.